Hi everyone. So this is going to be a brief lesson on continuous compounding. So I wanted to start off by kind of reminding you something that we said in our last lesson, which is that continuous compounding is when the number of compoundings n grows beyond all bounds. So rather than compounding every year or every month or every week or every day, it's constantly compounding, right? So it's a non-stop compounding process. And so this is something that you might not see in a bank because that's sort of a very manufactured process. But when you have more natural processes where, for example, inflation is an example, there isn't a set time when inflation compounds. It's constantly impacting and constantly affecting the prices of things. So the other thing I wanted to remind you of is here, which is essentially the compound interest formula. Recall that for a finite number of compoundings n, the actual value a is equal to the principal p times 1 plus r over n to the power nt. Here r is the annual rate, n is the number of compounding cycles per year, and t is the number of years. The other thing that we did in our lesson from last time, so we didn't actually write this, but we said it. We noticed that as n grows beyond all bound, or as n tends to infinity, p times 1 plus r over n to the power nt, that doesn't grow beyond all bound. It actually grows to p to the power pe to the power rt. So of course, e here is that number we've mentioned many times. It's called the natural exponent, or you can also call it the natural base. And it's an irrational number. It goes on forever, but it's approximately equal to 2.718. And so one of the exercises that we did in our last lesson was we looked at 1 plus 1 over n, so we built a value table showing that as n grows beyond all bound, 1 plus 1 over n to the power n approaches e. So in fact, e is by definition the base of the function that describes this behavior. That's why it's called the natural base or the natural exponent. So I just wanted to play a little bit with this formula. So I wanted to do a few examples. Okay. So let's say that we have the following question. How long will an investment at 3% compounded continuously take to double? Okay, so notice that here I'm not telling you what the size of the investment was. So I'm actually going to write that here because I want to point it out. Note, we are not given P. And what I hope you remember from one of the lessons from this week is it doesn't matter what the initial size of the investment is. It's going to take the same amount of time to double at a given rate. Okay, so here we don't know P, so let's just leave it P. The actual value that we want is 2P. We want our investment to double. I guess N is infinite. That's kind of a goofy thing to say. We don't know T. And R is given to us as 3%, so we will write it as 0.03. All right, so here we go. The actual value that we desire is 2P. P is how much we started with. We know that as the number of compoundings goes to infinity, this whole 1 plus r over n business turns into e to the power rt. So we have 2p is equal to p e to the power 0.03t. This is an exponential equation. I'm going to write that again because I just really want to continue reinforcing that this is something we've seen before, even if we've never worked with it in this context. Okay. And then we're going to start by dividing both sides by p. This is why it doesn't matter that we don't know what the initial principal was. It just gets factored off at the first step anyway. So 2 is equal to e to the power 0.03t. And now if two things are equal, then their logs are equal to. Okay. And now check it out. By the properties of logarithms, this exponent is going to pop out to the front like so. So we have the natural log of 2 is equal to 0.03t times the natural log of e. But don't forget, natural log is log base e. So the natural log of e is log base e of e, which is 1. So this is 1. So I don't really need to keep writing it. So really I have the natural log of 2 is equal to 0.03t. So all I need to do to get t by itself is divide both sides by 0.03. Now, this is a precise value. So that is, like, if I wanted the precise value, that's what I would leave. However, realistically, if you ask someone how long is it going to take for this to happen, you want an answer that actually is digestible, right? So we're going to round this to 2 decimal places. So again, just really pay attention to the number of decimal places that you're asked to round to. Okay, so here we go. So we have the natural log of 2, and then we're dividing it by 0.03. So this is approximately 23.10. Since it's money, since these are questions about money, you'll notice that a lot of the time we round to 2 decimal places, but it doesn't matter here really because it's years, where it's a question about years. So what we're seeing here is that an investment invested at 3% compounded continuously would have taken 23 years to double. Okay, let's look at one more example. Okay, so in this example, say that an investment of $1,000 compounds continuously at an annual rate of 5%. And so let's just answer a few questions here. So A, what is the value of this investment after 10 years? Okay. And then B, how long until this investment is valued at $50,000. Okay. All right, so let's see. So after 10 years, so again, I just want to stress here, we're looking at continuous compounding here, which means that the number of compoundings is infinite, right? So we can even write that here. So n, the number of compoundings, goes to infinity. We started with $1,000. T is unknown. Oh, actually, excuse me. In A, T is 10. And R is 5%, which is 0.05. So all we have to do in A is just find the actual value. So we want to know A, and it's P, which is 1,000, times e to the power RT. So here R is 0.05, T is 10. So it's nice and easy to multiply by 10, so let's just do it. It's 1,000 e to the power 0.5, right? 0.05 times 10 is 0.5. So let's go ahead and punch this in. So we have e to the power 0.5 times 1,000. Okay, so this is $1,648.72. Okay. All right. B, how long until this investment is valued at $50,000? So in this problem, you know A. Let's actually write that here. We know what the actual value is. We still have that P is 1,000. We still have that R is 0.05. But in this case, we are solving for T. Anytime that you encounter a question where the lead is how long or how much time, you know that it's the time variable that you're solving for. Okay, so here goes. So 50,000 is equal to 1,000, that's our P, e to the power RT. So I don't know T. This is an exponential equation. I'm going to write it again because I want you to never lose sight that that's what this is. And then from here, we've done this before. We're going to divide both sides by 1,000. So we have 50 is equal to e to the power 0.05t. And now, like we do with all exponential equations, we'll take the natural log of both sides. And by properties of logarithms, the exponent can pop out to the front. So we end up with the natural log of 50 is equal to 0.05t times the natural log of e. But like we talked about in the previous example here, the natural log of e is just log base e of e, which is 1. So we don't even need to write it anymore. All we need to do to get t by itself is divide both sides by 0.05. So this is the precise answer, but of course we're all curious, like how long is this going to take? We want to hear, is it going to be, 30 years? Is it going to be 100 years? How long is this going to take? So let's punch this in and get an approximate answer. So we have the natural log of 50 divided by 0.05. So that's approximately 78.24 years. So here's kind of a fun fact, and I'm going to write this maybe up here in this little blank spot. But one way to interpret this is that if you think about inflation, so the rate of inflation fluctuates tremendously. It depends on economic conditions, but an inflation rate of 5%, like you could say, well, that's about what inflation is. It's actually a little bit high for inflation, but it's not that outlandish. So if we say that inflation kind of hovers right around a rate of 5%, what it means is that if you go back 78 years, right? So maybe in our grandparents' or our parents' lifetimes, if we go back 78 years, $1,000 78 years ago has the buying power of $50,000 in today's money. So now that's assuming that inflation kind of was around 5% over the course of that 78 period. but it's kind of crazy to think about. So I'm going to write that here kind of as food for thought. So this means, for example, that if inflation averaged about 5% over the course, let's just say, of the last century, that $1,000 78 years ago had the buying power of $50,000 today. So the things that you could buy, so kind of think to yourself, if you had $50,000, what could you buy? Well, those sorts of things are the sorts of things that you could buy for $1,000 78 years ago. So continuous compounding is a really great model for inflation. That's where we'll stop this lesson. For our next lesson, we're going to take the same model of continuous compounding and say, why does it need to only apply to the world of money? Why can't it apply to the natural world where we see things growing and decaying? So that's all I have for you for now, and I will see you next time. Bye.